All right, guys. So today I'm gonna try to solve the following question here. Um, it's a kind of like a test question. It's something that you might encounter in maybe a computer science class, like an introductory architecture class, something that goes beneath just programming. We're looking at the bits, we're looking at the ones, the zeros, that kind of thing. A lot of these classes kind of play with the math aspect of these. Keep in mind, I'm not a professional. I don't work in this field. I'm just looking at it from the academic side of things. This might be a question you would have on a test or something like that. This is just me going off of the solution I came up with when I was proposed this problem. So it concerns something called bit fiddling. At least that's the kind of word that I learned for this topic. You're basically playing with bits. You're trying to solve this math puzzle using these binary operators. So here are some of the binary operators that we're going to be using. They're on the screen now. And you might wonder, okay, what are these? Well, this video, I'm not going to get in depth with what these are. I'm going to assume that you already have some knowledge on them. But I'm going to do a quick demo just for anyone who might be a little bit behind. So, what is and? We might think, okay, well, in past classes, you might have learned that and looks a bit like this. Okay, well, in Boolean algebra, is A and B the same as A times B? So if I had 3 and 2, is that 6? Or is 3 and 2 a bit more like 5? Are we adding them? Are we multiplying them? What are we doing? Well, the answer is really neither. I'm going to show you. So if you imagine you have 3 in binary, 1, 1, and 2, 1, 0, and is the AND gate, that looks like this, right? And you probably know the truth table for an AND gate. Also, I realize I'm writing crookedly, despite the fact that I have graph paper in the background. I will correct that in the future. I'm sorry. But basically, this is, so you're ANDing the bits together. So if I have 1, 1 and 0, 1, this means I'm going to AND the lowest order bit. And what is 1 and 1? 1. Then I'm going to AND the next pair of bits. That is a 0 and 1 is 0. Oh, I wrote this backwards. Excuse me. 2, for all of you who caught that, good job. 2 is actually in this direction. So if I ANDed the first or the lowest order bits, 1 and 0 is 0, and 1 and 1 is 1. Okay, so 3 and 2 is 2. Wow, that's weird, but yes, 3 and 2 in this context is 2. But I'm going to be thinking of it more like this and this instead. And that makes it a lot easier to see. Oh, well, with ANDing, anything that's a 0 just kind of disappears. You're not passing the value through. And anything that is a 1, you are. So you can think of ANDing kind of, it clears whatever bit is a 0 and it sets whatever bit is a 1. But if it was this direction, if it was 1 and 2, then you'd really have the opposite problem and you just get 0, 0 because each of the zeros is kind of rooting the other 0. But you know all that with AND gates. You've studied all these gates. We're just now putting them into longer bits or, bits, then nibbles, then bytes. Then maybe we're going to do like 16 bits or 2 bytes. We're going to do it a lot longer. That's actually why I have this graph paper here. So we might be able to do some operations with the numbers like this. So let's begin. Let's look at the prompt we're trying to solve. Now, it's basically telling us bits 15 through 12. That really means the first 4 bits that you're going to see. then there's a gap of 4 bits, then there's another 4 bits, and there's another gap of 4 bits. So it's really, what I do in these situations is we're talking about 16 bits. So I'm going to go ahead and just number my bits. And so we got 15, 14, 13. We'll fill in the rest of those. And 0. Hopefully that's not too small. So what it's saying is we want these bits. Wait, I think I did that wrong. 15 false. We want the first 4 bits to be set. And we don't care about the other bits. We're not saying these have to be clear. We just don't care about them. And then the next set is going to be here. So we want to check whether this amount of bits is set, and we don't really care about these guys. So the part of the prompt is asking us to try and evaluate in parallel. Evaluate in parallel kind of means I want you to imagine you're taking this chunk of bits here and just moving it below. Now, you're not really moving it below. What you're really doing is you're kind of creating a copy of it moved below. So what you're really doing is you're gonna basically create a new variable where you've shifted this amount to the right 8 times to get it to move that way. And then you're gonna AND it to the first value. So here's the idea. I really am just interested in taking these and sticking it underneath, and we're gonna AND them. So I'm just gonna say that's 15, 14, 13, right? So the separation is right here, I believe. Let's just count them. 0, 1, yep. And then, okay, so there's a separation there. So we're just going to kind of note it in our heads that there's a bit of a separation there. And now we're going to fill in our values. We're not actually going to fill in our values because we don't have any. So we're just going to say that we're interested in these. Now we're imagining that these guys are 1s, right? Because if these were all 1s, regardless of what these were, if I ANDed these 2 together, so think of this AND as like, ignoring the little indexes in blue, we're just ANDing them, we should still end up, these wouldn't actually be 0s, excuse me, I need to make that distinction. It's not there's 0s, it's that there's we don't care about these, but we do care about these guys. So we've extracted them. Now we don't know if they're 1s, but whatever they are what I want. And now the interesting thing about this is that technically what we're doing is this is our original number, this very long one, as you can see. That's our original number, that's x. And then the next part is really x shifted to the right 8 times. Because I took this, I shifted it to the right. What really gets filled in on the left side is going to be 1s. That's assuming that our left shift does take into account the sign bit for this question. I'm going to assume that it does. We'll see how it goes. So we are going to imagine that this x shifted to the right 8 actually has these kind of like they're 1s. They should be there. If they're not 1s, if the leading bit was not a 1, then these would be 0. So we want to imagine that these are either 1s or 0s depending on what was leading. I'm going to draw these like invisible little 1s just to imagine that they're 1s. Maybe later we'll change them to 0s if we need to see what else would happen if it wasn't set. Now some of you might be wondering, why did I draw the 1s there if I said that doing things in parallel is taking that and moving it over? Well, it's because this is still a 16-bit number. So if I've taken this and shifted it to the right 8 places, 1, 2, 3, 4, 5, 6, 7, 8, I have to fill in something from where I left. And some types of computers will fill in 0s, some will fill in 1s. So back to the problem at hand, I have put 1 on top of the other. The x's indicate that I don't care what those values are. They could be 1s or they could be 0s. They're not guaranteed to be 0s. We're just praying that the yellow highlighted is indeed 1s. So if I kind of fold it on itself or shift it over by 8 to shift it over by half and AND it to itself, that's what this AND is for. these should all be 1s. Now, we don't know what they are. So this operation has successfully checked if these match each other. If any one of them is a 0, then we're going to have a 0 here, and then that will change what we do. But for now, we're going to assume that they're 1s. So we're kind of praying that this is, we're praying that this looks a bit more like 1, 1, 1, 1, and I don't know, 0, 0, 1, 0. We don't care. We're praying that that's what it looks like, but we really don't know. Okay, so now that we have this here, whatever this is, perhaps we said that x is equal to x ANDed with a version of x that is shifted to the right. So that might be maybe those are our instructions. Maybe that's what we're going to say. So x equals itself ANDed to itself moved over to the right. And that might be our instructions. But like I said, that does mean that there's invisible 1s all down here. Well, invisible, but implied 1s, right? If there were indeed 1s here, there should also be 1s here. If not, there won't be. If there was a 1 here and 0s and 0s, there still would be leading 1s across here. But we're going to have to see how those come into play with our problem as we go through. So we now have hopefully 1s for sure here, although we're not too sure what they are. And there's some ugly values that I don't really want those there. Here's the thing. I know that I have trailing 1s in front of me. If I were to now take this number and shift it here to clear out all these, usually when you compare things, you want the numbers you're checking to be in the lower order. Because at some point I could compare it with just a 1 or a 0 or something, and we would know that for sure. So I'm going to imagine now that we're just going to take x and we're going to shift it to the right 4 times. This isn't really necessary. This part is not part of the instruction. That's just me saying this is now x. But I'm going to shift x to the right 4 times. So what happens? Imagine this moving to the right. Now, as it moves, it continues to fill in those invisible 1s that I talked about. So now we have our numbers here. So I'm, the check marks that I was saying, these guys are now here. Do we know whether they're 1s? We really don't know what they are. So I guess maybe I should have replaced these with question marks. But the same things are being moved over. So maybe what I'll do is I'll put a check mark. So these are the values that we've collected from before. We're really hoping that they're 1s, okay? But as far as these go, all these guys, if my first bit was 1, which we really hoped it was, all of these should be 1s. And in fact, if these 2 were 1s, the way I've done it, I've completely made these guys obsolete because this is down here. And by shifting this to the right, I've completely removed the need to even look at what these blank spots were. They're completely cleared. So with all this, all of these should be 1s. They should all be 1s. Now, we don't have any if statements. We don't have any if statements to say like, hey, if this is all 1s, can we just call it a day? We don't have that. What we do have, the closest thing we have to an if statement is the not operator. The not operator basically says there are only 2 values. There's true and false. False means there's no power. There's nothing. There's no bit set. True means any bit is set anywhere. Okay? So what I can do is I can, the not operator basically takes the opposite of the truth. So if something is all 1s, and I say not all 1s, then I'm going to get a 0. But we really don't want that. What we want to do is say, if you are 0, then I will return the opposite of what you are. It sounds crazy, but Currently, we're all ones, but check this out. What if I said not x? Okay. So remember, these guys are all ones. Well, they should be. If they weren't all ones, so let's imagine this guy is 0. Now we would have 0, 0, 0, 0, 1, 0, 0. And then if I said to you, return not x, so not this kind of x, but like return the exclamation point. In this case, where one of the 4 bits was a 0, then by the time we get to the bottom of our program, it will output a 0 because 0, 0, 0, 0, 1, 0, 0, 0, if you take the not of that, it will give you a 0, as in the fact that it had a little power makes it true, and then the logical not with the exclamation point will output false. Now let's go back to the case where, in fact, the highlighted bits were 1s, and this means that the variable x so far should be all 1s. So I'm going to flip the bits. I'm going to flip all the bits so that they're all 0. So 0, 0, 0, 0, 0, everything is 0. So these guys should be 0, and the leading trail of 1s that I should have had if I started with at least a 1 should be 0. So now I'm all 0. So what is not false? All zeros means false. X is false right now. What is not false? True. So this statement is going to return a final 1. It's going to return a 1 with a bunch of zeros in front. Notice that I didn't have to convert this with masking or shifting to get a 1 in the 1's place. All I need to do is to check if something is nothing, use this. If it is nothing, it's going to tell you 1. It's going to do the opposite of what you are. It's not flipping your bits, it's checking, are you true or false? So this works. We know that if I had an x where there was a 0 somewhere up yonder, then a 0 would be in, well, actually, all of these would be zeros. Like, even if these were 1s and whatever. Oh, wait, wow, no, that's worse. I would have complete zeros. Let's just say I had, like, this. Wait. My brain hurts. Yeah, I would end up with this. From here, these check marks, actually, these would sadly be zeros. If I shift it to the right, these would sadly be zeros. If I then flipped it, it would look a bit more like this. And these are very, very true. There's very many 1s there. So the not truth is falsehood. The only way this actually works is if I had every single one of these pieces as a 1, because this would shift here. And I would have 1s. The leading 1s would follow me around. This, if it's not obvious, put a line here. This is a result of ANDing these two. So this is this and this, which equals this x here. Then I still have that x. Now what I've done is I've shifted it to the right 4. So all these obsolete bits, whatever they were, if they were 0s and 1s and whatever the hell they were, they are gone now. I did draw some like pretend example bits here, but they're gone because I shifted to the right 4. And my leading 1 should have given me even more 1s. When I shifted, the holes were filled in. Then what I did was I said, not x. So this was x now. If I didn't make it clear, this is x now. This is x shifted to the right 4, but I've set it to x. I've said x is this now. X is itself being shifted. So now that this is x, maybe I should write it this way, or I don't know, x is itself shifted to the right 4. Now we have that is my value. Now I want to utilize the comparison operator with the not. This is the hardest part. This had to take some time to think. But the idea is I've made them all zeros. I've made them all into falses. this is only going to be false. This is only going to be a string of zeros if it came from a string of ones, which only can happen if these were ones, right? So there's no way in hell this would not be zeros. This point, they all have to be zeros if I've done it correctly. Now that they're all zeros, I can say this is false. I want to use this operator to tell me what is not false in this world. 1. And that's what the prompt wanted. It said, give me a 1 if these are set. And we've gone through the whole thing and we found out that we can get to this point only if and only if those are both set by this logic. Then I can give you that 1 that you wanted.